SwayamPrabha. Digital India. Educated India.
Good morning. I'll present today axial flow steam turbine. I have indicated here a real multi-stage steam turbine having HP and LP, means low pressure stages. In low pressure stages, the blade's height is considerable with larger twist than the HP. In HP section, blades are mounted between the hub and the shroud, and the blade height also considerably low as compared to the LP section. Hope you would appreciate the construction of a real multi-stage steam turbine. With this introduction, I'll present now the steam turbine. Contents of the lecture are axial flow steam turbine, impulse versus reaction turbine, simple impulse turbine, pressure compounded impulse turbine, and velocity compounded impulse turbine. Let me present you about the introduction of a steam turbine. Please note that a turbine can be of axial or radial flow machines. However, here we'll restrict to the axial flow steam turbine. Steam turbine consists of rows of nozzle followed by the rows of rotating blades. Indeed, the steam is the working medium here. Furthermore, please note the pressure ratio in a steam turbine is much higher than that of the gas turbine. Furthermore, steam turbine rotates at constant speed even at different loads, which is accomplished by governing or the controlling of turbine. Regarding power cycle, or if you consider a power plant, Rankine cycle is the operating cycle, and here the water is pumped to the boiler, and then boilers converted superheated steam, which is expanded in a turbine and then condensed in a condenser, rejecting heat to the atmosphere. Again, the water is pumped to the boiler, completing the cycles. I have indicated here the cycles, that is pump, boiler, turbine, and condenser. We get work output from the turbine because of expansion of steams, particularly superheated steam. Now I have indicated the Rankine cycle in TS diagram, where 3-4 is the pump work and 4-1 is a heating of water at constant pressure to produce the supersaturated steam, which is expanded in the turbine. That is 1-2 is the expansion process producing work output, which is used for production of electricity. And then again 2-3 is the cooling of exhaust steam in the condenser, rejecting heat to the atmosphere. And this completes the cycle. Now, if the condenser is used, then discharge pressure of a turbine can be made below the atmospheric pressure, and thereby we can increase the work output by decreasing the discharge pressure. I like to mention here about types of steam turbine. Here I like to say that I have already discussed about impulse and reaction turbine while presenting the chapter on gas turbine. However, let me discuss again for sake of completion. So types of turbine that are used in practice are impulse or reaction turbine. The impulse turbine can be classified as where the pressure in the rotor remains constant, while in impulse reaction turbine, or simply known as reaction turbine, the pressure in the rotor decreases. Furthermore, this impulse or reaction turbine can be used in single stage or multi-stage. Now I will discuss about simple impulse turbine. The single stage impulse turbine consists of a row of nozzle and a row of rotor blades, is known as simple impulse turbine. This is also called the Lovell turbine after its inventor. Here steam is expanded in several convergent divergent nozzles, producing high speed jets, and this high speed jet is deflected within the rotor, decreasing the absolute velocity. Since the pressure in the rotor remains constant, I can say the relative velocity would remain unchanged. That means W2 should be equal to W1. Now, because of deflection of the relative velocity within the rotor blade, there will be change of angular momentum transferring energy. I have already stated that during this process there will be no pressure drop or enthalpy drop across the rotor blade. This is simply the characteristics of an impulse turbine, particularly a single stage impulse turbine, which is known as simple impulse turbine. A single stage impulse turbine is shown in figure 1. Please indicate the casing of the single stage impulse turbine. The casings have the hatched portions. First, steam will enter to the nozzle and it will be expanded in the convergent divergent nozzles. After the nozzle, the rotor would follow. The rotors are mounted on the rotor disc, and the rotor disc would be in turn connected to the rotating shaft. After the rotor, steam will be exhausted through the exhaust port. Now there are glands for packing to prevent or to minimize the leakage loss. Furthermore, please note that the impulse turbine blades can be recognized by their shape. They are very symmetrical. So I have indicated here the impulse turbine blades are symmetrical, having entrance and exit angle around 20 degrees with respect to the tangential directions. So I have also presented here the pressure and the velocity distribution within the nozzle and the rotor. So this is this value represents the inlet velocity and this is inlet steam pressure. Now within the nozzle, pressure would increase. After that, so all drop of enthalpy and the pressure would occur within the series of nozzle. After that, the pressure would remain constant. So within the rotor, the pressure remains constant. And if we consider the absolute velocity will increase in the nozzle section, and then it will decrease in the rotating blade. And this is the exit velocity or the exhaust velocity. And this exhaust velocity is considered as kinetic energy loss. So please note that the exit pressure of the steam, which is equal to condenser pressure, and the exit velocity of the steam, which represents the kinetic energy loss. And here the kinetic energy loss will be considered as a loss. That's why in simple impulse turbine, the exhaust velocity is high. Thereby, the aerodynamic losses of a simple impulse turbine are high as compared to others, particularly as compared to the reaction turbine. Thus, this is one of the disadvantage. The disadvantage of a simple impulse turbine is that the aerodynamic losses is considerable. Let me continue with the disadvantages of a simple impulse turbine. The kinetic energy of the jet from the convergent divergent nozzle cannot be efficiently converted to energy, leaving a loss as high as 10% or more. Further, the rotational speed is also very high, and it increases with the pressure ratio. Thus, the controlling of a simple impulse turbine is difficult. In order to reduce the rotational speed of the simple impulse turbine, particularly for a high pressure ratio, compounding or multistaging needs to be done in one of the following ways. 1. Pressure compounding. Second, the velocity compounding, or combination of pressure and velocity compounding. Please note that the concept of multistage in turbines has not been discussed while discussing gas turbines. Here, in this chapter, while discussing the steam turbine, I'll introduce the concept of multistage. I have already indicated that when the large pressure drop is available, it is inefficient to utilize in a single turbine stage. Furthermore, please note that a single stage utilizing a significant pressure drop or enthalpy drop would lead to a larger diameter or a high rotational speed. Therefore, turbine with large pressure drop employ more than one stages. That is, we are learning to the concept of multi-stage. Let me discuss now about pressure compounded impulse turbine. I have indicated here that to alleviate the problem of high blade speed, of a single stage impulse turbine, the total enthalpy drop is divided among many single stage impulse turbine in series as indicated in the figure here, figure 2. Note that the total pressure available I have divided in different simple turbines and they are put in series. So regarding construction, let me explain that this is called diaphragm. Diaphragm holds the nozzle, which is followed by the rotor. Rotor is mounted in the disc, which is connected to the shaft. And this is the high pressure section. And this part is the low pressure section. And if you take the central plane, circumferential plane or circumferential section stage on the paper, what I'll see is indicated here. N stands for the nozzle and M stands for the rotating blade. So there is nozzle followed by rotating blade. Please appreciate the blade which are indicated by black. The blade sections is symmetrical, having the same inlet and exit angle, and they are very simple in its construction also. Please note that the velocity drop in every rotor are the same. So almost in the, if we consider the 8P section, enthalpy drop in every nozzle is almost the same. That's what I have indicated here. This is the pressure as pressure variation. So the pressure decrease in the nozzle, then it's same in the rotor, then again decreases in the nozzle, same in the rotor, and again decreases and remains the same. And if you see about the steam velocity increases in the nozzle, then again decreases in the rotor. Again in the next stage, steam velocity increases and again it decreases in the rotor. If you see, the magnitude of changes remains same in every stages. So ultimately it leads to the low exhaust velocity and the rotational speed also decreased. Such turbine is called rotate turbine after the name of inventor. Furthermore, please note the important point that the inlet steam velocity to each stage are almost equal and the speed ratio remains constant as the enthalpy drop in each stage is almost same. Thus again I'd like to state this point that here the speed ratio for every stages remains invariant and the inlet velocity to each stage are essentially the same. So it's a repeating small stages. So this is the most efficient method of compounding. Furthermore, one should note that pressure gradually decreases here and thereby the volume of steam increases and hence blade height needs to increase towards the low pressure side of the turbine. Further, pressure compounded impulse turbine does not suffer from serious leakage problem as the pressure remains constant within the rotor passage. However, it is expensive due to combination of large number of stages. Let me discuss now about velocity compounded impulse turbine. I like to say here, one of the method to use a multi-stage expansion of impulse turbine is velocity compounding. Here, the high jet speed from the nozzle is efficiently converted to energy output by employing many rotor blades separated by rows of fixed blades. Thus, there will be rows of rotor blades separated by fixed blades. Now, the function of the fixed blade here is to guide steam without shock to the next row of moving blade. So I'll present a figure, which is figure 3, that will describe the construction of velocity compounded steam turbine. Figure 3 illustrates the construction of a velocity compounded impulse turbine along with distribution of pressure and velocity. This is the schematic of velocity compounded impulse turbine, where you can find the nozzle, and here 2 rows of moving blade are mounted on the turbine discs, on the same turbine discs. And these moving blades are separated by the fixed blade. So I have indicated here, usually 2 or at most 3 moving blade rows are mounted on the turbine disc. Now, if we take a circumferential plane, which is the central circumferential plane, and stretch on the paper, I'll find the blade profile. So N stands for the nozzle, followed by the moving row of blades, and then fixed row of blade, then again moving row of blade. Now the pressure here, total pressure, will drop in the nozzle, and then the pressure would remain constant in the moving and the fixed blade. Thus, in this region, the pressure remains constant. Regarding the velocity magnitude of velocity increases in the nozzle, then it decreases in the moving blade, then again it remains same in the fixed blade, then again velocity decreases in the following moving blade. So this is the exhaust magnitude of exhaust velocity or exhaust of steam. So please note that, as I have indicated, we generally do not use more than 2 or 3 moving blades. This is because as the second or third moving row develops only a fraction of power generated by the first moving row of blades. C.G. Curtis first proposed the velocity compounded impulse turbine, and thus it is referred as Curtis stage. Furthermore, as I have indicated, in Curtis stage, the total enthalpy and the pressure drop occurs in the nozzle, and thus the pressure would remain constant in all the rows of moving and the fixed blades. Now regarding features of cartridge stage, I like to say that it is associated with a significant enthalpy and pressure drop. Furthermore, they are simple in construction and thus economical, compact and reliable in operations. However, frictional loss is relatively high, and hence the maximum efficiency achievable is relatively low as compared to the reaction turbine. Lower speed ratio. Furthermore, the Cartins turbine is often used as a first stage in a high pressure turbine because it can accommodate a significant pressure and enthalpy drop. In a reaction turbine, often we stage the first stage as the Cartridge stage, which causes a large enthalpy and pressure drop. Thus, this arrangement reduces the leakage problem. In this lecture, I have discussed about axial flow steam turbine, impulse versus reaction turbine, the concept of multi-staging, that is pressure and velocity compounding, their pros and cons. Thank you for listening.